Hello everyone. Today we are going to learn about electromagnetism. First of all, moving electricity makes a magnet, and a moving magnet will create electricity. Who would have guessed? So you will get to see both of those things in this lab. Anytime electricity flows through a wire, it creates a magnet. How come you didn't know this? Well, the magnet is so weak that you probably never even noticed wires being magnetic. Let me show you that. This compass will be attracted to a magnet because it itself is a magnet. Notice. And then, so what happened was, I connected the electrical current and it flowed all the way through the wires as a complete circuit. Then when I unhooked it and broke the circuit, then the electricity stopped flowing and it stopped making this wire a magnet. By itself, this wire is just barely enough of a magnet to slightly lift a paperclip. So how do we make that electromagnet stronger? One way is to coil the wire. A coiled wire is called a solenoid. Depends on where you're from as to how you pronounce this. Down here in the South, it's solenoid. But I think the rest of the country pronounces it solenoid. It's just a coil of wire. If you hook wires to the ends of your solenoid, it makes a big difference in the magnetic field. This electromagnet is strong enough to lift a paperclip, just barely. One of the hallmarks of an electromagnet is that it can be turned on and off. For example, when the electricity is not flowing, this solenoid isn't a magnet. But when we connect the electricity, it is. Once the wires are disconnected, there might be a little residual magnetism left, but it quickly dissipates. So how do we make the solenoid a stronger and more effective electromagnet? By adding a ferromagnetic core. That's a piece of iron that runs through the middle of the solenoid, or the coil. Then, when the electricity, whoa, it wasn't even close and it affected it. Look at that. It turns it completely around. And when it comes to picking up paper clips, wow, it lifted quite a few. On a regular magnet, there's a north and a south pole, and these are attracted accordingly to a compass. Remember, the North Pole points north. But wait a minute, now it's pointing south because the North Pole of the compass is attracted to the South Pole of this magnet. And as we move the compass around the magnet, you'll see the compass follows the magnetic field lines. The compass is doing the same thing that the magnetic field does. So let's see if an electromagnet is the same. Hey, look at that. The exact same pattern is followed. Therefore, since the south pole is being attracted, this must be the north pole of the magnet. Even though the electricity is flowing here, the entire screw turns into a magnet. And the magnetic field lines are the same as around that bar magnet you just saw. So add magnetic field lines to the solenoid below to show the magnetic field. It's drawn the same way that a bar magnet would be drawn. And just like a regular magnet, it's not very strong in the middle, but it is strong on the ends. Therefore, the poles of an electromagnet are the strongest, just like the ends of a regular magnet are. And notice once again, we can turn this magnet off by stopping the flow of electricity. It took a minute for all the magnetism to dissipate as the domains slowly randomized within the iron. So right now, the right-hand side of the electromagnet is a south pole, and the left-hand side of the electromagnet is a north pole. What if we reverse the current? What if we run the electricity backwards? Let's switch these two wires. Check it out. Now this end is a south pole and this end is a north pole. Pretty cool, huh? Notice that for this compass, the north pole is correctly painted red. unlike the rest of my compasses, which seem to be painted backwards. So when you reverse the electricity in an electromagnet, the poles also reverse. Now let's try making an electromagnet with more coils of wire. Is that a stronger or weaker electromagnet? Well, this compass sure is strongly attracted. Let's see how many paper clips we can lift. Oh, wow, that's a bunch. So this is a much stronger electromagnet. So far we've been using all 4 batteries for a total of 6 volts. But what if we only use one battery with 1.5 volts? Well, the compass is still attracted, but what about the paper clips? Aha, we can lift quite a few, but not quite as many. Let's see, right now we have 4. And when we use all 6 volts, now I've lifted 7. Finally, when I use all 6 volts and 2 coils of wire, wow, that's a lot. 12 paper clips. Now let's talk about some uses of electromagnets. Large electromagnets are used to separate and lift scrap metal. The electromagnets can be turned on and off to lift the metal and then release it. Electromagnets are also used in MRI machines. That stands for magnetic resonance imaging. And electromagnets are used in speakers, motors, DVD drives, doorbells, generators, copy machines, and many other electronic devices. Now, we just saw how moving electricity makes a magnet. Now, let's look at how a moving magnet creates electricity. So now what I've done is I have attached this solenoid to wires which are attached to a galvanometer. A galvanometer will detect very tiny amounts of electrical current, even smaller than what can be detected by a voltmeter. So I have a very weak magnet, and you'll see as I run the magnet across the coil of wire, the needle just barely moves. Well, that's not enough to see, so let's use a much stronger magnet. There we go. See how the galvanometer moves much more strongly. Moving the magnet induces or causes a current in the circuit. So you have caused a current by induction. The magnet must be moving in order to generate electricity. As long as the magnet's not moving, then no electricity will be generated. You'll notice that when the magnet is moved back and forth, the electric current moves back and forth, and so it switches direction. You'll also notice that the speed of motion makes a big difference in the amount the galvanometer moves. When it's moved slowly, it moves a little. When it's moved fast, it moves more. This is why when you use a credit card, you must swipe it quickly through the machine in order to generate enough current from that little magnetic strip on the back for the machine to actually be able to read your card. Now we're using the solenoid with 2 coils. Does that give you more or less motion on the galvanometer? Looks like more to me. So more coils create more electricity, and fewer coils create less electricity. What if we remove the ferromagnetic core and just use the solenoid? It's a little harder to drag it across, but you'll notice there's much less electricity being created. Yeah, I don't really see any. And as you've probably already noticed, when I move the magnet one way, the galvanometer moves one direction, indicating the current's moving that direction. When I move it the other way, the galvanometer moves the other direction. You should now be able to answer the rest of these questions on your own.